She's a senior studying mathematics who will be starting her PhD in pure math at the University of Texas at Austin. She has worked on a number of research projects in geometry and topology. And notably, she has an NSF-funded project at Cornell. Lisa's talk tonight will focus on mathematics as it relates to topological surfaces using an example that I think we'll be able to understand, the arcade game of asteroids. Let's welcome Lisa Piccirillo.
Great, yeah, so like you mentioned, what I want to talk about today through a specific example is what abstract math is really about. What is it that mathematicians do and think about what's going on up there in Carney? So I want to take a look at this theorem, and I mean that very literally. Please, dear God, do not read it, just look at it. So there's a lot going on here, right? We have like these terms, we seem to be adding them. There's a fraction, actually they're like nested fractions there. We've got an inequality, there's like things being raised to powers with some subscripts. Maybe you remember that that might have something to do with derivatives. We're not really sure. There's a logarithm up top, there's things down here, and so we sort of squint at this. I hope you're still not reading it. And we decide that we know what this is. This is math. That's math, I found it. Okay, And I don't want to assume that I know how you feel, but I know when I go to a talk and some sort of disembodied garble of symbolic notation goes up on the screen in the first slide, I like throw up in my mouth a little bit and like doodle in my notebook for the rest of the talk, right? Like nobody likes this. You perhaps don't like this. I don't like this. Mathematicians don't like this. Nobody studies math because they're really jazzed about taking a first derivative or stuff that looks like that. And so if this isn't what mathematicians are excited about, but this is math, we decided, we know this is math, what are mathematicians excited about? And so, as Tommy mentioned, for one, they're excited about arcade games. So this is Asteroids, and I think this is a really interesting game. And what I think is interesting about it is the way that the asteroid spaceship moves around in space, which I'm going to call Planet Asteroid, and it'll become clear why I'm calling it a planet in the future. But when he goes out the top of the screen, he comes in the bottom, right? When he goes out the left, he comes in the right. I want to take a closer look at that. So here's our spaceship out the top and the bottom. And so there's sort of funny business going on at these two orange points, right? Like everywhere within the screen, not near that blue boundary, the spaceship behaves exactly as like if we put a hedgehog on a table and let it run around. It would behave just like the spaceship. And so these two orange points are really the issue. It's like when we get to the orange points, the spaceship suddenly gets the ability to teleport. But I'm not super interested in assigning properties to the spaceship. I'm more interested in assigning properties to the space. So instead of saying that the ship can teleport, I want to say that in Planet Asteroid, those 2 points, those are actually the same point in space in Planet Asteroid. And similarly for our blue friend, in the top at the bottom, those 2 blue points are the same point in space in Planet Asteroid. We can do this for all of those points, and we can do it continuously. And as much as I love any excuse to use a rainbow gradient, that's really cumbersome notation. So when I want to say this, I'm just going to decorate things, sets with the same decoration. And what that means is that those 2 sets of points are really the same sets of points in space in Planet Asteroid. We go out the left, we come in the right, and exactly the same story. So okay, great, I decorated Planet Asteroid. But this is not really that much more helpful to think about, right? Because I'm still saying like those points up there are the same point in space as these other points down here, but it would be really helpful for me living, in this space if those points actually occupied the same point in my space. So I'm not saying 2 of the same points in space are occupying different points in space. So let's try to physically make that happen. We used to be playing arcade games in, an arcade game screen, but now I want to play them on a piece of paper. And being a piece of paper, it can fold and bend. So let's start to wrap it around. We can bring those 2 edges closer together until they're actually joined. And that's great for us because now those 2 just points in space that were all the same, they're now occupying the same points in my space. At least the top and bottom edges are. So that's good. Let's keep going. We can bend this cylindrical thing around, bend it further, and the picture gets worse and then gets better. And we get something that looks like this, right? So now I don't have any of this funny business, any edge of the table nonsense. All the points that are the same points in space in Planet Asteroid are also the same points in space in Planet Lisa, right? I'm sort of now happy. And if you think about the way that spaceship moves around in this donut, and be careful, this is not a very filling donut. If you eat it, it's not going to help you. It's really just a glaze on a donut. There's nothing in there. But the way that spaceship moves around on this planet is the same way as it moved around in the screen. So really we haven't lost anything here. And mathematicians have a word for this guy. We call it the torus. Not that important. So I want to think more about this, but just a little bit of background. This comes from a branch of math called topology. Lots of mathematicians define topology differently. I like to think of it as geometry, but where we don't care about distance, which can seem like a really strange thing to think about because you all took geometry and you probably answered a lot of questions like, what is the length of the edge of this triangle and how far apart are these 2 points in the coordinate plane? And that's all about distance. So what happens if we don't have distance? Well, if I don't care about distance, then I can take my points in the coordinate plane and I can like stretch them apart or pull them together because I don't care how far apart they are, because I don't care about distance. So what that means is I can take all my geometric objects and pretend they're made of silly putty or rubber or your favorite stretchy surface, substance, whatever. So to a topologist, a square is a circle because I can take my rubber squishy circle and give it corners and now it's a square. Similarly, a cube is a tetrahedron is a sphere, right? I can build these out of Play-Doh and squish between one and the other fluidly. So it's starting to sound like my subject might not be that interesting because I'm saying, well, we care about geometric objects, but actually they're all the same. And so is anything distinct to a topologist? And the answer is yes. There's a couple things I'm not going to allow you to do with your silly putty geometric objects. And I'm not really going to let you do anything kind of violent with them. So you're not allowed to like tear it or rip it or poke holes in it. That's like a worse change than like a nice smooth squishing of it. And I'm also not going to allow you to introduce self-intersections. So no like taping it to itself or sort of smushing it together where it wasn't already together. So to a topologist then, planet Earth is actually distinct from planet Asteroid. If you go home and you build him out of Play-Doh, him the sphere, you're not going to get him, you're not going to be able to get a torus without either joining like a tube together or poking a hole in it. So back to asteroids. We looked at planet asteroids, which I'll now call planet asteroids number 1, and that was not so bad, so let's change the rules a little. Now I want to go at the left-hand side of the screen. I want to come in reflected on the right-hand side. I want to make those 2 points be the same point in space. So what I've done is sort of reflected across a horizontal axis. And by the way, I'm leaving the top and bottom the same behavior as we had before. Similarly, all of these points match up in the new rules of planet asteroid. Maybe my arcade game will catch on, I'm not sure. And so we decorate it like this. And just like before, I would rather that any points that are going to be the same in space be the same in my space as well, because that's going to help me think about it. So we go to cylinder, just like last time. That's not so bad. And it's working pretty well to do what we did last time. But we get here, we're almost glued up to a torus. And there's a little bit of an issue. If you check the orientation on these boundaries that we'd really like to glue up, because that would be a torus, and we're comfortable with those now, they're pointing the same way. I mean, the wrong way, right? They're not, the decorations don't match. We can't glue them together like that. We have to do something else. So, all right, you get to stretch things as much as you want, though, right? Because I'm a topologist. So perhaps we just did it wrong. And you go back and you unfold it and you try some other stuff. And you try some other stuff for a while, and it's not going to work out. And I claim it's never going to work out. We'll talk about that more later. But let's suppose you really want a picture because you don't like this distinct points in space are the same point in space. It's very confusing. We like pictures. So maybe you've gotten here, and you notice that small, that smaller boundary component, it looks a lot like that bigger boundary component now. The orientations are correct if it were just somehow like inside the tube. And so you really want a picture, so you break my rules. You introduce the self-intersection, you poke it through itself, and you connect it up at the bottom. And this space, planet, whatever, is what mathematicians call a Klein bottle. And I just want to call like a lot of attention to the fact that it's not quite a picture, right? We have these self-intersection points. And what that means is we've sort of actually reversed the issue. We're now saying that points that are the same point in planet Lisa are distinct points in planet asteroid. And that's an issue too. It's just a little better for me because at least all my points are only appearing once. All right. So we've seen a couple things we can get from changing the rules of asteroids. And we might ask ourselves, well, instead of just like trying a bunch of things, what sorts of things could I get in general? What sorts of planets can I have just from an asteroid's universe making some rules? And I claim that this is a really hard question, but you might think it's actually not so bad. I mean, we play asteroids in a square, right? You need pairs of edges to identify. There's only so many. But remember, I'm a topologist. A square is a circle, and also a square is an octagon. And now there's 4 pairs of edges. And there's a lot more ways to identify them. And also a square is a 100-gon. And so there's not going to be a good way to just like enumerate all the possibilities here and look at them all. We're going to have to be more clever if we want to know the sorts of things that we could get in Planet Asteroid. So 100-gon is a lot more complicated than a square. And things sort of seem to like spiral out of control when we go down that way. Like I don't even want to think about identifying up 50 pairs of edges. So let's like dial it back. We're more comfortable with a square. And can we get back even further? So a geometer is not going to let you have a polygon with non-zero area and 2 edges. But I'm a topologist, and I don't care if you curve your edges. So this is our friend the bigon. Those dots are just meant to show that those are vertices in this bigon. And we can definitely play asteroids in that. So let's play asteroids with these rules. Can anyone spot what planet this is using like the folding, curving methods that we've been using? Oh, Tim's not in here. I know he goes, yes, he is. Tim, what is it? Sphere. Yeah, this is a sphere, right? We can like curve it around. Oops, too many. We can curve it around into the board, and it joins up and it becomes a sphere. So those rules with asteroids give us Earth. And so what about these rules? And I'm not going to sort of bother you about this one, because this one's a lot harder. Mathematicians call this a real projective plane. And this is another guy that we're not going to be able to get a perfect picture of in my space and in the space we live in. But let's try. So all I've done here is sort of like bowed out the bottom, so it looks like a bowl, but I haven't really changed anything. And I'm noticing now that those 2 red points are the same points in space and Planet Asteroid. So let's bring them together in Planet Lisa. It's now just kind of figure 80 along the top. And it looks like I've changed the identifications, but I really haven't. I'm just saying like that's like the bottom side of the top edge, and I'm turning it orange, but the bottom, the identifications are correct here. I'm just calling attention to them as like separate parts now. So if we want to join up the red ones, we can sort of like clap them together up above that red point. So let's do that. And what that does is it stretches that other component out to become those 2 orange curves. And we still don't have anything bad happening, but it's about to happen. No self-intersections yet. But if I want to bring those 2 orange cones together, I can't really, not orange cones, I'm sorry, orange edges together. I can't avoid that sort of edge marked with the red label. But let's just bring them together along that edge to get a sort of picture. And so maybe Planet Asteroids, I guess we're on number 4, kind of looks like this. But we have all these self-intersections along that orange line. And this is called the real projective plane. Not going to talk too much about it. So we have planets, and we can look at them, and we can play asteroids on them. And we can be like, well, I don't think that one looks like Earth. Can we do anything else with them? This is, after all, a math talk, so let's add them. Mathematicians call the adding of planets this operation of connect sum. And it's really like the most childish notion of addition you've ever heard. We poke a hole in them, we give the hole an identification, just like usual, and we join it together. But another way you could think of this is you squish the planets together, and then you take away the overlap. So we really just combine them. So the connect sum of 2 tori gives us this new planet, or it looks new. I don't think I've seen this before. And this is a 2-hole torus. So that was not so bad. Let's try adding other stuff. If we add a sphere and a torus, it goes like that. I'm a topologist. I like to squish things. Let's squish that sphere, squish it some more, and we're back at a torus. So that's kind of interesting. I added 2 planets together, and I got back one of the planets relatively unscathed. So what happened there? I think that's a great thing to think about. And I want to come back to this question that I asked before. What sorts of things can you get from just taking some screen that you want to play asteroids in and changing the rules about what happens when you go out various parts of the edge? And we're now prepared to at least see what the answer to this is. And so the sorts of things you can get from changing the rule of planet asteroids are exactly the things that I can get from sticking together some combination of spheres, tori, and projective planes. And the converse, anything that I can get by sticking together spheres, tori, and projective planes, you can get by making rules on planet asteroid. And those sort of seem like 2 very distinct questions. We have an arcade game, and we have me squishing together things made of Play-Doh. And it is, in fact, very surprising and a significant result that those are exactly the same. So I gave a talk similar to this in January to a middle school math class. And it went really well, and at the end, a boy stood up in the back, and he was like, "That was awesome! That was not math." And that's actually kind of an astute point, because this doesn't look anything like what we saw on the first slide, or probably what you did in school. And so was it math? I mean, I would say yes. I would define math as really just the asking and answering, or attempted answering, of interesting questions, which seems like a nice definition, but that's also how you could define any academic discipline ever. So let's clean it up. I would define math as the asking and attempted answering of rigorously defined questions. So what do I mean by that? Well, precisely. Remember this guy. This is the Klein bottle, and I told you that using the asteroid instructions that we had for him, you can't possibly fold him up without self-intersections or poking holes, right? But I didn't prove it, and maybe you believe me, but perhaps you don't. So you could go home and get your bed sheet and spend the next 2 hours like trying to fold this, and it's not going to happen, but that doesn't mean that it can't happen. It just means you've been insufficiently clever in trying to make it happen. Perhaps maybe there's some way to do it you didn't think about. But while you were spending 2 hours playing with your bed sheet, you were thinking about this, and you thought of some questions, and you realized that there's a lot of stuff that I haven't told you. Like, I said you can't have self-intersections, but what does that mean exactly? I mean, what if I folded the bed sheet really tight, so two parts of the bed sheet got really close together at the fold, but they're not really touching, but they're kind of arbitrarily close. We can get as close as I want. Is that a self-intersection? And I'm not allowed to poke holes. Well, okay, maybe I won't get out my scissors, but what if I gathered the bed sheet really, really tightly, because it's really stretchy. So I can gather it into a point, a tiny point, like a point of measure zero, and we don't know what measure zero means, but if that point almost doesn't exist, can I separate that? Does that count as a rip? And what does it really mean to exist in this space anyway? And when you start to try to understand what I'm talking about and what you're thinking about, the words and the language that you use are going to really quickly dissolve. You realize that I haven't actually explained anything. I haven't really defined anything. I've really broadly said, we play asteroids and we make some rules, and don't let it touch itself. But what does touch itself mean? And it's all very poorly defined. And this is because a spoken language is not meant to mean exactly the same thing to everyone. Words are meant to have context and multiple uses, but what we want to do is take these abstract ideas and talk about them concretely so they mean exactly the same thing to everyone. And that's where all that garbage on the first slide comes in. That's the formal language of math. Because spoken language doesn't allow us to communicate in some sort of absolute sense, mathematicians have created this other language that does. And so while this can be what's frustrating about math, what all that horrible business you did for 12 years in public school was, and what's on the first slide, it's also what makes math really fascinating and sets it apart from every other discipline. In all other disciplines you have theories, maybe well accepted ones, but in math we have theorems. We really prove things. Everything we talk about, is completely universal and sort of built up from axioms, and it's a really cool way to think and to talk. Just to illustrate that, this is a proof. Again, this is a slide you shouldn't read, but this is a proof that you can't embed the Klein bottle into R3. Didn't define embed, didn't define R3, didn't really define the Klein bottle, but this is a proof that you can't do it. And to close, I just want to say some words about how we think about math and how we teach math. When people find out I study math and I'm getting a degree in math, I get 3 responses, which are, I really hate math, I'm really terrible at math, or you're nuts. I'm not going to address the third, but to the first, I would say that I don't think that anyone is bad at thinking about interesting problems and thinking creatively and posing interesting questions. And also, I don't think that anyone would like learning French if all you did was memorize a huge list of nouns and verbs, but you never traveled to France, or you never read French literature, or you never spoke French. So I think if we change the way that we teach math and we interact with math to talk more about the ideas that mathematicians think about, to talk more about cool problems, and we use the language, we use the nouns and verbs to actually form sentences and dialogues, then that would change how people feel about math, how they feel about their ability to do math, the way they consider going into careers that use math, and really sort of make the field more accessible for people who find it very closed. These are my references. I just want to call attention to this. This is The Shape of Space by Jeff Weeks. It's my favorite math textbook, perhaps after Elements. And it's like no math textbook ever. You could like sit on your couch and read it like a novel, and I really recommend you do. It's about a lot of the stuff that I talked about today, if any of that was interesting. It requires no math background. It's chatty, it's brilliant, lots of pictures. You should go buy it. Thanks. Oop.